shove this somewhere. Okay, yep, it's working. So let's get to, first of all, just a very brief lesson for today. And then I want to talk a little bit about how we're going to deal with the numerical methods using Python. Okay, so where are we here? This is it. Okay. Today we're just gonna, like I said, it's gonna be a little bit of an introduction to using some Python and the book, so that you understand how to navigate the book. And this week is largely the preliminaries, just dealing with some of the error that we're going to have to calculate, as well as Taylor series. I think I hinted at that last time, but we're actually going to get into it on Wednesday. Oh, so today is relative and absolute error. And you probably already know this, but I want to make sure that we formally deal with this. So in our book, we're going to have this some number that we're going to approximate with some other number. So for example, at the bottom, you see pi. Pi, you probably have used this in the past. 22/7 is approximately pi. I don't know if you've ever done that, but if you type 22/7 into a calculator, you get 3.1428. Not exactly pi, but pretty close. And so that's an approximation of pi. It's one of the Diophantine approximations for pi using continued fractions. That's from number theory, so it's not really all that relevant, but for this class, but it's kind of an interesting thing that we're going to use. 25/8 is another approximation of pi, as well as 355/113. So we want to know how close those are to pi, and so we'll use this idea of absolute error and relative error. Absolute error is, of course, how far you are away from the actual truth, whereas relative error is relatively, speaking in terms of a percent. How close are you to the truth? Hopefully you have a calculator. If not, doesn't matter. We have our computers. Yeah, despite what my syllabus says, we're going to be using our computers quite a bit in this class. So if you have a computer, you might want to have it at the ready. But let's actually compute some of these. I'll do these on a hand calculator, and then we'll pretty quickly switch over to Python. So I want to give you a little introduction to Python as well. So this first one, so we have these three that I wanted to do here. 25 divided by 8, I'll do on this hand calculator. I'll write what I have. That is 3.125. So that's close to pi. We all know what pi is, but on our calculators, I'll get what at least this calculator says pi is. Once I find my pi key, I guess I should have used, oh, I see it. Sorry. So let's see, does that give it to me? So on this calculator, I have 3.154159265. 3.5 is the next, but they have 4. So this isn't even exactly what pi is. So if I want to know how close I am to pi, I would just take so using this formula, the p here is the actual number. The p with a tilde over it is what we're using for an approximation for the number. And so I'll take the actual pi on the calculator, subtract off 3.125, and I get the absolute error. So the absolute error, p minus p tilde, is equal to 0.01, I guess, 659. I'll go that far. I mean, anytime we use a computer, we're getting an approximation for many of the numbers that we're doing. Even the value for pi that I'm using here is an approximation. And so this is just going to give us a way of describing how close we are to the truth. And so that's what this stretch is about here. Let's do 22/7, and then we'll talk about the relative error after this. Let's get absolute errors first. So 22/7 is on my calculator. Whoops, clear. 22/7 is 3.142857. And so let's take pi and subtract that. So here, I'll just write this down, 3.142857. By the way, 22/7, it repeats itself. So if you were to write 142,857, it would continue to repeat that 142,857. So there's 22/7. Let's subtract that from pi. So let's see, subtract from pi. Oh, come on. keep pressing the wrong button here. It gives it to me in scientific notation, of course. So let me just interpret this for you. 0, 0, 1, 2, 6, 4, 5. So you can see that that is considerably, it's closer in absolute terms. This is closer to the actual value of pi. Let's do this last one just for fun. So 355 over 113. And I got 3.141, whoops, 159,292 on the calculator. So you can see this is much closer. And like I said, this comes from, if we were to have a number theory course here, you could study the continued fraction for pi and these Diophantine approximations for pi. But for us, we're just going to see how close this is in absolute terms. So subtract this from pi. And I got, wow. Okay, so this is going to be 0.000000267. So each one of these numbers is an absolute difference between pi and the approximation. So that one is pretty good. So if you really want a close approximation of pi, you can memorize that 355 over 113. That's much better than 22/7. But of course, you probably have access to a calculating device that has some approximation for pi stored in it. Anyway, each one of these, we could talk about the relative error. So to get the relative error, you just divide this by the actual value for pi. So for this last one, divide this by pi. And I got, okay, this is so small that it's almost, I mean, it's, as a percent of error, it is almost zero. So I won't even try to write it down. But let's do this first one just to get an idea for what we're talking about. 0. And of course, when you're talking relative error, that gives us an idea of how close we are relative to the truth. And if the truth is a big number, then of course the absolute error being a large number might not be that bad. So this will, let's see, divide this. So I'm going to do this first one, divide that by pi, and then we'll get to the computer and it'll be much more fun. So this gives me 0.5%. So 0.528% is how close this is as a relative value. So you'd be able to compare one number to another, even if those numbers are different in orders of magnitude. Of course, these are all comparing to pi, so you can compare those approximations pretty easily. Okay, so let's take a peek at our, let's see, here it is, syllabus. Well, not on the syllabus, the textbooks. So we have these two textbooks, T-time numerical analysis and programming for computations. And then on our, whoops, where is it? There it is. So here we have the homework assignments listed, and the homework for next time is this first one. When you click on this page, you should get a little check mark that you can check off. I just want to jot these down so I can remember what the ones that we're supposed to do are, because I was going to do some of them with you. So 3A, B, C, E, 4A, B, C, E, 7, 8, 9, and 11. So they're available to you online. So let's go back here. Okay, so there it is. So there's the homework. And you also have this link to Google Colab. If you haven't already got a Gmail or Google account, sorry, we're going to have to do this well, it's not entirely necessary. So here are your options. When we're using Python, you can either use Google's Colab, or if you prefer, you can, I have on my, here, I'll show you. Let's see, Jupyter, just a minute. Jupyter. So I have Jupyter Notebook installed on my computer. So you could load it that way if you don't want to be beholden to Google. You could do it that way. So Jupyter Notebook, or there are other ways to get this. But this is a really easy, quick way to get access to Python notebooks. And as I mentioned on Friday, the only thing that I have that I'm a little bit leery about using Google is that when you do start a new notebook, and actually every single time you type in here, it offers to let you use AI. So see, it's like, hey, you could just generate this with AI. And I'm like, well, I really don't want to at this point. So, you know, I guess it is what it is. We're living in this world where we have this AI available to us. So anyway, there's that. So you'll need access. You don't have to do this while I'm doing it today. I just wanted to show you what it looks like and also orient you to our textbook because there are some weird things with our textbook that you should be aware of. So, so let's take a look at the textbook first. This is what you'll get when you download the textbook. Is you'll get this. This is the T-Time numerical analysis, and you'll notice that they have a good deal of information where they say in octave. So this octave is just another. It's not. It's like Python, okay, but it's not as broadly used. You could download Octave, and I actually toyed with the idea of having us do this, but I thought instead of having, this is this esoteric programming language that's used for mathematics, let's use Python, which is just as good, if not better. Actually, it's probably better. So we're going to use Python. Anytime it says octave, just in your mind, think Python. And the commands are going to be a little bit different, but don't worry, I'll work with you about that. So most of this, so here's the homework just to get you started on it. Let's see, let me look again. It's numbers 2, 3, A, B, C, and E. So here's number 2. It's easy enough. You can compute it's exactly what we just did. You can do that yourself. Compute the absolute and relative errors of the approximation of pi using 3 instead of pi. And then some of these you can do on a hand calculator if you want, or you can do them in Python. But then E, so you see that symbol there is the symbol that, like the icon for Octave, this programming language, but we're going to use Python. So anytime you see that little thing that looks like a, I don't know, it's a little circle with some squares floating around in it, we're going to use Python instead. So same thing goes with these. So I thought, let's get started on this because it's interesting to see how this works. So give me a minute here and I'll get set up. And if you have some sort of a Python available to you that you can use now, that would be great. You can follow along, or you can just follow along and see what we do here. So like I said, with number 2, I need to also think about, I haven't decided how to turn in the homework because of course, you know me, I'm old school, and so I love paper, but there's no need for paper in here, is there? So I need to figure this out. So you do homework however you want to. We'll discuss on Wednesday how we want to get it turned in and go from there. But I'll definitely have a quiz on Wednesday, so just be aware that I'll have some sort of a quiz on Wednesday, and that quiz will look similar to all the other quizzes that you've had when you've had me in class. Sorry, Matthew, you'll have to figure it out on Wednesday because it'll be the first time, but it won't be hard. Don't worry, you'll get an A on the first quiz, I guarantee. Well, I can't guarantee that, but if you do the homework, you should do well. Okay, so anyway, just a couple of minor details about Python is that, well, not form, wait a minute, sorry. Let me make this a little bit bigger. So if you are following along, is that, let's see. Okay, good enough. If you are following along with your Python notebook in Google Colab, then you can do this. If not, I don't know, it would be good to note this, is that Python doesn't, just like most programming languages, doesn't have all of its packages and modules and whatever loaded automatically. And so we need to import the important stuff. And so just to get us started for this, I think this is all we would need, is we need to have the math package or whatever they call this in Python. So I'll start off by saying from math import asterisk, which means import everything, just bring it all. And what that's going to get us is everything from the math package, including exponentiation. I don't know, there's a variety of different things that, like the pi, we need to be able to use pi. So what I thought I'd do is get us started with a few of these. And then maybe we can, let's see, I need, you know what, I need text here. Let's throw some text in here. This is problem 2. So we'll do, no, you can do problem 2 on your own. Problem 3. Let's do problem 3. So there's my text. Let's see, and then I want code. Oh, also, you need to run each of these cells, and to run them, you press the little play button. There it goes. The first time you run something, it's going to take a little while to get things all set up. So just be patient. That little circle will go around. And now, there, it's all set. So, and it says it only took 0 seconds, which it didn't. It took longer. So anyway, from math import star, what that's going to do is it makes available all of the math code for us. So now we can do things like we can have the number pi. Pi is just, well, that's pi. If we just do that, you'll see it'll spit out 3.14159. But I don't want to do that. I want to do problem 3. Let's do part E. Here, we'll do this. Print. I know this is kind of in... let's see, how do I do this? Is this a single quote, double quote? Let's try this. So this is probably a little bit inefficient, I should say, but we'll do it anyway. So here, P is equal to pi. So we'll do that. So I'm just going to follow. If you look on the left, we're supposed to let P equal, I'm not, pi to the -7th. So exponentiation, if you're not familiar with Python, is done by a double asterisk. So pi star star -7 should give you pi to the -7th power. And then if I want p tilde, that's spelled out what this symbol up here. If you don't like writing the word tilde, you could do hat. I don't know, call it something else, but that's this number I want to type in here. So P tilde is going to equal 10 to the, star star -4. So we're going to compare these two numbers and see how they look. Now I suppose we could just print them. So print P and P tilde and see what happens. So let's run that cell just for fun. And you can see that this is for part E. That's why I printed the letter E. So if you were going to do this entire homework set using Python, you could just print each one and then have the stuff. But anyway, this here is pi to the -7th. And this, of course, is 10 to the -4th. And we're supposed to compare these to get the absolute and the relative error. Now, here's the thing about what I'm about to do is once I do it for this particular part of the problem, you could easily cut and paste, and you could do the entire problem 3. I don't know why I restricted myself to just parts A, B, C, and E. You certainly could do the entire problem set. I mean, almost with no effort after what I'm about to do. Okay, so there's that stuff. Now we'll do, let's see, abs error. We'll call it abs error. Wait, can I do an underscore with a variable? I think I can. Error. Oh, interesting. They even suggest. Incredible. Well, that's what I was going to type. Oh, equals. How can I get it to do this? Tab? Amazing. Okay. Okay, this is too good. I didn't realize how, well, that's exactly what I wanted to do, is I wanted the absolute error to be the absolute value of P minus P tilde. So I guess that the artificial intelligence is a little bit too good. I also, though, I didn't want to just do this. I wanted to do the relative error. So relative, let's see if it'll do this for me. Relative error. Yeah, amazing. So it's suggesting exactly what I wanted it to do, so I might as well just tab through that. Well, what am I even doing here? Well, I guess that my job is to just encourage you to learn about all this stuff, right? But you see what it's done for us, don't you? It's the relative error is the absolute error over the original number. Now, technically, I would like to put the absolute value of this number here. And that's only in the off chance that this number here that we were comparing our estimation to, if it's negative, we would want the relative error to be a positive percentage. All right, well, let's see what happens when we run this cell now that oh, you know what? Actually, I do want more than it's giving me. I also want to do this, is I want to put here, I'm gonna rearrange this stuff because I don't like the way that this turned out. So let's delete that. So I'll put in quotes, absolute error, and then comma this, and then comma, and then relative error there, just so that it's error. There we go. And then outside the, there we go. And then I'll put comma rel. Wait, what just happened? Okay, and so then I'll have the relative error. Okay, there we go. Now this will make me more happy. Uh-oh, what happened here? Something is unmatched parenthesis. Where's my unmatched parenthesis? Hold on a sec. There's something wrong with this. I thought I could just, do I need single quotes for these? Hold on a minute. Let me try putting single quotes. Single quotes, and then I've got this. Single quote. The heck? Let's try this. See if it'll like me now. Fix error. Okay, I'll just add it to fix error. What's wrong with this? Hold on. It says unmatched parenthesis. Did I put an extra one at the end? I just can't see it because it's too big for my screen. Just a minute. Oh, there is an extra one. What in the world? Oh, okay. Now will it like me? Okay, that's much better. Okay. Losing my mind there. You would think that it'd be easy to see. I guess I need to make it full screen apparently. Okay, yeah, so isn't that nice? So we have the absolute error here, the relative error. So we're talking almost 70%, almost 70% off. So those aren't good. That's not a good approximation for this particular number. So that's that part of the homework. There's another interesting thing that that the book brings up, and that's the idea that because of round-off error, because machines can't store the number pi perfectly, or even the number square root of 2. So those numbers aren't perfectly stored in memory. Because of that, you get some weird things that happen when you're dealing with a computer. So if you've taken a computer science course, I'm sure you've already done something similar to this, but it's fun to do it again. And so we have this whole list of equations. This is problem 11. It's the last of the problems you have to do. I guess I should look and make sure that the other things make sense as well. But this last problem is really interesting as well. I want to get you started on that. So you'll notice that it says all these equations are mathematically correct. For example, the first one is a pretty simple arithmetic expression. The second one, letter B, involves a logarithm and an exponent, exponential and logarithm there. So you can see all of these are correct, or you can just trust that they're correct. But Python and apparently Octave will, because of round-off error, will not recognize them as being this correct. And so it just wants you to experiment with these. So let me just show you how that works. So give me a sec. I'll set this up. So this is problem 11. So maybe I'll just throw some additional text in here real quick. So this is problem 11. Okay, great. Now I'll put code down here. Okay, so this will be print. Let's just do A. Okay, great. So just I'll do 2 of these. Oh, wow. Just a minute. Sorry. Okay, tab. Amazing. I like my when I've used Python with like it's gotten so much better than it used to be. I was just in the dark years ago. And then with the Jupyter Notebook, if you've used that, you know that there's some autocomplete that's really nice. But this is beyond autocomplete. I feel like this is predictive. Like it's like saying, I think you want to do this. And I'm like, well, yeah, actually I do. But anyway, so here we go. We've got A, B, and C that we're going to print. Very nice. And then we'll put in between, I will just print. So what they want you to do, let's go back here so you can see. Let me zoom in. Can I zoom in? Yes, I can zoom in big. Is they want you to type in this equation to see if Python can recognize that that's a true equation. So taking this letter A, and this will illustrate this idea of round-off error, which I'm sure you're familiar with, but bear with me. We got to go through these preliminaries. So let's see, can I make this, that's too small. Hold on a minute. There we go. This is better. Okay. Yeah. Now, where did my stuff go? There it is. So, so for letter A, I'm just going to print that exact equation. So 2 times 12 is equal to, and to get the Boolean expression, this idea like it's going to evaluate whether they're actually equal, you use a double equal sign, just like it says in the text up here for this particular textbook. Don't forget that exponentiation is done with a double asterisk for Python, and then 4 times 9 minus 21. So this should be a true statement. So let's find out if it recognizes it as true, and sure enough, it does. So basically the output is just true. Well, we're going to do the same thing for a couple more, just 2 more. Let's see, letter B. Oh, letter B, maybe E. Yeah, I'll do B and E, I guess, just to, yeah, we'll do both of them. Okay, so so let's do B, and then we'll do E. So B, sorry, make it higher, there. So we want to do, and the reason is I want to just make sure that you see how this is done. Now this is part of the math package, and we already loaded math. So this is EO. So we're going to print again. So print, and we're going to print EXP. So EXP is the is e to the x. So exp of 3 times, and then the natural log is log, which I know you might think of as being just the log base 10, but I don't know why this thing keeps popping up. I don't want to see all that mess. Okay, but then I have a double equal sign, and then I want to set this equal to 8 and see if it's true. There, that's better. So that's what I'm going to type is e to the 3 times log, which is natural log of 2. Are those equal? And algebraically they are, but notice that Python says no, that they're false. It's false. And you can see why. This is because of round-off error. If we were to print, let's see, I can just copy this, copy, and just print these 2 numbers. So here, I'll just print them in the same block there on the same line. So you can see them, there they are. So notice that because of the round-off error, in this, you can only have so many digits. How many digits is this? This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16, so it's pretty good. 16 digits or 15 after the decimal place, but it's not exactly 8. It's off by a little tiny bit. So we have these errors that occur. So the other ones, I don't know that I need to do the other one. I mean, with each one of these, like that's the floor function there. That's what that means. And you can define functions. Let me see this g of x. Let me just see if I can remember how to do this. Just give me a sec. Here's this, up, up, up. Yeah, let me go to D. So give me a sec. So print D. Okay. So, oh wait, first of all, I need to, why does it do that? Okay, so let's define a function. which function is it? G of x, there it is. Define g of x, let's see if I remember my syntax here, if this works, is equal to the cube root of x squared plus x raised to the 1/3. Let me just see if this works or if it will complain. Print g of 1. Let's see, did it like me or did it not? It did not like me. Define g of x. Oh, I gotta remember how to do this. Oh, will it tell me? Fix error? Yeah. Oh, colon. Maybe I need a colon there? Oh, colon. Ah, yes, yes. Okay, where's my, what in the world? Oh no, it did something to my code. Oh yeah, this is what I should have done here. Just a minute. Can I get rid of that? It messed up my, oh no. Oh, it's making suggestions. I have no idea how to use this. It's so weird. Like it's got these pluses. I see what it's saying. It's like, no, what you need to do is define this and then, okay, well, that's the correct way to define a function. How do I get rid of this though? Bottom left? Okay. Okay, good. Okay, now I can fix it. Excellent. Okay, yeah, very good. That's right. Functions in Python. It's been a little while. So return this. Return this. Excellent. Well, thank you to Python. Did that still work? Still work, yeah. Okay, so that worked. So anyway, you can define a function, and then now that we've got that function defined, you can check to see whether or not when you plug in 1 plus the square root of 5/2, I suppose we can even define this. Let's define this, as long as we're doing this. Let's see, let's define this. We'll call it phi, because that is the mathematical constant phi, or phi, sorry. 1 plus squirt, is squirt work? We're going to find out. Yeah, apparently it does. Squirt 5 divided by 2. And then we can do g of phi. And does that equal this? Does that do it? Let's find out. It's true. Oh, wow, it's true? Seriously? I mean, it should be true, but I guess I thought that with that square root that we would have some round off error, but apparently it's not enough of round off error to throw it off. So interesting. Yeah, this is the golden ratio. It's this mathematical constant. Okay, very good. So let me just double check the rest of this and then we'll get started on the next section. But this is really all you have to do for Wednesday. It's not going to be hard. I want to make sure we got 7, 8, and 9. Okay, so 7, 8, and 9 are also, like I said, I just want to make sure that you're okay with if there's any weird syntax that we need to make sure that we can do in Python. So I think we're okay with this number. You can compute that yourself. And there it is. And then it says that this is an approximation of 1/pi. We want to find the absolute and relative errors for that. So compute this. It's almost exactly what we did up here. So that's easy. You're going to do it in Python, though. So anytime you see octave, say Python. And then compare this to 1/pi. And then this next one, I can't remember what is special about this. Oh, yeah, these are just, can you compute these things? So, I just noticed there's one thing there that is a problem, and that's letter D. Letter D is, I wonder if that one, just a minute, I'm curious to see if we can compute that. So most of the rest, I think you can puzzle through. You can figure out how to compute, like cosine, that's easy enough, right? Arctangent, and by the way, this is the ceiling function for letter F. So ceiling function you can handle, probably figure out. But it's that I is equal to the square root of -1. I wonder if it'll take that. I'm curious. I know that I can import a package that will interpret it correctly, but I don't know that we want to go there. So give me a sec. let's just see if this works. Negative exp evaluated at the square root of -1 times pi. All right. I wonder if this will work. Okay, so let's enter. Math domain error. Yeah, sorry. There's a symbolic computation package for Python that I've used in the past that would handle this, but this is not. Yeah, the math package doesn't. So I guess you can skip letter D, since letter D isn't going to work for us. By the way, if you're curious what the answer is, letter D is 1. E to the pi I is -1, so negative e to the pi I would be 1. So, but the rest of this you should be able to do. I don't see any other problems with any of the rest of this. So really, all this is for 9 is just, try some things out in Python, and it gives you some stuff to play with. So that's that. All right, so, and I think, is that it? Yeah, 9 and 11. So before we go on to the next little topic, what sorts of concerns or questions, fears do you have? I know I'm just throwing this at you saying, hey, you're going to learn Python. It's going to be easy. But especially with, yeah, this looks like it's not going to be as painful as it has been in the past. With the, not yet, not now, not yet. We'll talk about that on Wednesday. Okay, but is it? Yeah, it's pretty straightforward. Yeah, but you've done some computer science stuff. You did Java. Okay, so Java is the computer. Yeah, so did they use an interpreter here or something? Or is it like this web based? Yeah, for Java. Okay, so you used, yeah. That's what I used to do with Python. Is I would have you download Spider or the Jupyter Lab, but this seems good. I don't know. Yeah, what do you think? Exactly. That's what I was going to try to figure out for Wednesday, because I guess I had in mind on Friday. I thought to myself that I would just have you submit things on paper, but that seems dumb. So uh, let me figure out what to do about the homework for Wednesday. Just do this, and I'll let you know Wednesday. And I should say though that the homework that is due Friday you will do on paper for sure. You'll see why in just a minute once we get done with the discussion about this, because it's not Python. So other things that we need to worry about or talk about this. Yeah. So I'm actually, when I first discovered that this was so, I guess, driven by AI, autocomplete, and all this, I was a little discouraged. But I think that this will make it more smooth now, because some of the problems that I remember from past versions of this class, I think that this will actually make it easier for me and for you. So, which is good. All right. Well, let's change gears just a little bit, because we're basically this whole first chapter of our textbook is preliminaries, and so we need to deal with another preliminary. It's going to take a little bit more time, perhaps, in this Python business. In the old days, the Python would have taken forever. But before we do that, let me just mention this. I don't think I put this up here before. Is that in the real world? So most of us are coming from a sort of an analytic background, analytic mathematics, where you're dealing with calculus. You have the functions. You can do derivatives. All, basically everything that's given to you is this perfect analytic sort of information. And the real world isn't like that. Real world, we don't have those nice analytic functions. Like if we're measuring something about temperature differences, we might have the data, but we don't know the actual function. And the function might not be an analytic function. So calculations are usually based on data. And so you're given a data set and you're supposed to do some calculations. And so that's really where the power of numerical methods is. It's not from taking the sine of x and computing the area under the curve. It's taking an unknown function based on some data and computing the area under that curve as best we can, or approximating it. So what we're going to be caring about is errors, which is what we've been talking about today. How close are we to the truth? And so each time we do come up with a new method, we will talk about how close can we expect to be to the truth. And so we will use relative and absolute errors to describe that. And then the second thing is speed. How fast are we going to get to the truth? Or at least how fast will we get as close as we can? Is this going to take all day, or is it going to be instantaneous? Modern computers, it's going to be pretty instantaneous. However, we could generate some pretty big problems that will take all day. So can we predict about how long it's going to take? So those two questions we're going to be answering using mathematics. So how close can we be, and how fast will it take? Now, one of the tools that that we're going to be using to answer those two questions comes from calculus. And so most of the methods that we're going to be using are based on calculus. So we're going to be using your calculus knowledge. But the thing that probably will bring the most dismay is that the primary tool that we're going to be using are Taylor polynomials and Taylor series as a sort of a springboard to coming up with our formulas. And so in addition to dealing with all these errors, we're going to have to also deal with this as preliminaries. But this isn't too bad. I thought we could get started today and then slowly deal with it on Wednesday, because I know that it's not your favorite topic perhaps from calculus. So anyway, I'll just remind you of some language and do one example today, and then we'll cut you loose and we'll resume on Wednesday to finish up all the examples on the Taylor polynomials. So the Taylor polynomials, just to remind you what a Taylor polynomial is, it is a polynomial that is approximation of of a function at a point. And the properties that it holds is that it is a perfect match to the function at that point, up to whatever degree you're producing the polynomial. And what that means is that it'll be exactly the same function value, exactly the same slope, exactly the same second, third, fourth derivative, up to whatever degree the polynomial is. So that's what's so special about this. And then the way that you compute it, though, is, let's see. No, let's skip that. No, we'll do this. No, we'll do this. This is what we'll do. We'll do this, and then we'll call it a day. So this will take plenty of time. So tangent line problem is the simple version of a Taylor polynomial, because a tangent line is just a Taylor polynomial of degree 1. Degree 1 meaning that it is perfect at the point in terms of the function value and the slope, and that's it. So let's go ahead and do a tangent line. So I want to find the equation of the tangent to the curve y equals x cubed minus x plus 2 at this point. So I'll give a minute to try this out, and I will switch over to Notability because it'll be easier for me to write. But you remember this, maybe you don't. If you don't, just relax for just a minute, because someone here will, hopefully, and we'll get it done. Okay, let me just switch over to Notability so I can put this in here. Paste it. Come on. Come on. Sorry, why is it not pasting? I don't know why it's not. Just a sec. Go back here. I'll leave this up here and I'll fool around so you freeze the screen so you don't have to watch me flailing about here. Huh. Try again. Let's try again. Okay, finally got it. Sorry it took so long. I don't know why my iPad is not functioning the way I want it to. Let's see, switch this. Okay, there we go. All right, so you're probably already done with this. I need a tangent line. Let's find someone. We'll use the randomizer of terror. Give me a sec here. Random student. I know you're excited, Eli. Eli, do you remember anything about tangent lines back from calculus days? Well, how about this? Let me ask you this. What was pretty much the answer to almost every question in calculus? What was the first thing you always did? Calc 1. Ask your roommate. Okay, you can ask your roommate. What do you say, Briar? Do you remember what the first thing you usually did in calculus was? Yeah, take the derivative. You remember this, Eli? I know, it was too simple of an answer. You thought, no, it couldn't be that. Yes, you always take the derivative back in calculus, right? So let's take the derivative, y prime. So y prime is equal to, let's find someone to do the y prime for us. Matthew, can you do this derivative for us? Very nice, 3x squared minus 1. Beautiful. Okay, so we've got the derivative. Why would I care about the derivative? I think you probably know. I'll see if I can find someone here. Grayson, why is it that we care about the derivative? It's the slope. Yeah, we want the slope because we're looking for a tangent line, so we're going to get a slope. So let's do that. Let's get our slope. M is equal to, it's not 3x squared plus minus 1, is it? That's a common mistake, by the way, in calculus, beginning calculus students. They'll give me their tangent line, and they'll just throw this in as if that was the slope. But once you put that there, it's no longer a line, is it? That's a quadratic, and in fact, if you multiply that by x, it's cubic. So that I need a number for a slope. But you know what the slope is probably. Let's see, Roston knows. Roston, what is the slope at that point? 11. Where do you get 11? Okay, so you've got 3 times negative 2 squared minus 1, which is 11. Beautiful. So now you can see why Friday's homework, we're going to be doing a lot on paper. So it's going to be finishing up this review of Taylor series. Okay, so we've got our slope. I'm going to go through this point. Almost done. It picked Eli again, but I don't want to put you on the spot again. But Alyssa knows. Now that we've got the slope, we've got a point, how would you go about coming up with the tangent line? Okay, so you're saying y is equal to 11x plus b, and then you would solve for b? That sounds good to me. Let's do it. So negative 4 is 11 times negative 2 plus b. So that means that b is equal to 18. Is that right? Okay, so we got 18. So that means my final equation, 11x plus 18. Now, the thing about this is that's such a like a, I don't know, elementary way of going about this particular problem. I mean, this is what you would expect from a Calculus 1 student. We're not Calculus 1 students. We have other tools in the tool chest. And so we'll, to get you used to this, that we'll use this. And this is more like a Taylor series. So this is actually what's called the linearization of the function f of x. And so this is just a much more efficient way to do what we just did, multiple steps. So this is the same. I'll actually write this down over here on the slide or on Notability, that you have f of c plus f prime of c times x minus c. So let me just go back here, and I'll just write that down. Y is equal to f of c plus f prime of c times x minus c. And in this case, c is negative 2. So we have f of c, that's negative 4, plus f prime of c, that's 11, times x minus negative 2. That's it. Put a y there. These are the same equation. You might not believe me, so let's actually expand that one on the left. Y is equal to negative 4 plus 11x plus 22. And sure enough, you get exactly the same equation. So there's this easy way that for some reason, well, I know the reason, is because we want you to understand tangent lines. And so we pound it into your head, the tangent line equation in Calc 1. And then we sort of at the very end, we're like, by the way, there's this linearization formula. Oh, let's go on to optimization or something like that. Yeah, so you hardly ever, you might not even remember doing linearization, but we can use this to come up with formulas for the tangent line and other things. For example, we could do e to the x, y equals e to the x at the point 0, 1. Let's just do this really quick because this is kind of cool. Um, so let's use the linearization formula though. So where is my, here, I'll just write it down. So y is equal to f of c plus f prime of c times x minus c. That's the linearization formula. So take a minute and write down the equation for the tangent line to y equals e to the x at the point 0, 1. It's actually a really, I don't know, it's an interesting answer to me. Oh, sure. Yeah. There it is. There. We can see enough of it. There we go. Good. All right. So doing it the easy way, hopefully, we need to find the derivative of e to the x. So Cooper-Stiegel. Wait, there's only one Cooper in here. Cooper. I made the mistake. It's the next class. Are you in differential? Yeah. So there's two Coopers there, right? Okay. Yeah. Friday I was like, Cooper, and I was thinking of you, and someone else said something. All right, Cooper, what's the derivative of e to the x? Oh, it's our favorite function. It's our favorite function until we find out that it's not, there's not as great as we think it is because there's problems that occur because of that. But yeah, derivative is the same as itself. So now we can just plug this in. Y is equal to f of c. And by the way, the c here is that. So that's 0. So I need to know what is e to the 0. Let's see who's going to do this one for me. Wow, it keeps picking the same people. Maybe I should just pick for myself. Sam knows what is e to the 0. It's 1. Okay, very good. And then we need f prime. Oh, it's the same thing, isn't it? Because it's e to the 0 times x minus 0. So this tangent line is 1 plus x. Well, y equals, sorry, should get rid of that. Y equals 1 plus x. I think that's super cool. By the way, exponential function, one of the definitions of the exponential function is that it is the exponential, well, e to the x, I should say. E to the x, the definition of e is it is the number that has a slope of 1 at 1, 0, or 0, 1, sorry. That every other exponential function is either steeper or shallower. This is the only one that has a slope of exactly 1. But getting back to this, so this is the sort of start of the Taylor series. Let's see, what time is it? Oh yeah, perfect. So here I will put down, and this is what we're going to focus on Wednesday, is we'll focus on the rest of the Taylor series. But I just want to show you that if you understand this, you're 90% there for the Taylor series. So this is the basics. Now watch this. To get the rest of the Taylor series, you just keep going. Check it out. I have f of c, f prime of c. The next thing is going to be f double prime of c times x minus c squared. The next one is f triple prime times x minus c cubed. You might notice I've been leaving some space because there is a minor correction I have to make for each one of these. 3 factorial, 2 factorial. So there's a little glitch, but and this goes on forever, of course. Well, Taylor polynomial ends, Taylor series goes on forever. But if you understand what we did back here with these first two terms, it's not a big stretch to say, let's tack on another term with a square and then another one with a cube. We'll deal with that on Wednesday, though. And also, you'll do this homework. I'll have a little quiz that'll be like, find the absolute error for pi when I use, I don't know, I'll come up with something. But it'll be simple that you can do almost in your head. and I'll figure out how to deal with homework because it's going to be a problem throughout the semester. So just do it, and we'll deal with it later. So, yes, sir. Oh, let me stop the recording so that